this video, we're going to introduce the moment of inertia. So we said in the previous lecture that so Newton's law for rotational motion can be written in this form. So it's the sum of all the torque is equals to I times alpha, where I is called the moment of inertia and alpha is called the angular acceleration. So this equation here tells me about Newton's law for rotational motion. If you remember, we said that for translational motion, we can write Newton's law in this form. So it's just the sum of the force is equals to mass times the acceleration. So now we're going to be talking about how to calculate this I value. So I is called the moment of inertia. So most of the time, we're just going to look up this value from a table. So you want to make sure that you understand exactly where the axis is. So for example, you can see that in these first three examples here, the I value is calculated about a point that goes through the center of mass. So it's very important to know what the axis is. Now, if you look at this example here, so this is a thin rod. So here the I value is calculated about the center of mass. Meanwhile, in this example here, the I value is calculated through an axis that goes through one end. So you can see that there is a difference. So this is the I value about the center of mass. This is the I value about an axis that goes through one end. So again, you want to be very careful to know exactly what axis you're talking about when you calculate the moment of inertia. All right, so now we're going to see how we can apply some of these concepts to solve some problems. So basically, if you give me any system, if I know the sum of all the torque acting on the system, then I can use this equation to calculate what the angular acceleration is. So if you give me all the torque acting on the system, then I can calculate the acceleration. So again, you can see that in this example, this force is going to produce a counterclockwise torque. This force is going to produce a clockwise torque. So because this force is greater than this force, it means that the counterclockwise torque is going to be greater than the clockwise torque, and you end up having an angular acceleration that is in the counterclockwise direction. So most of the times when we solve problems, if you know what the sum of all the torque is, you can solve this equation to get the angular acceleration, which is alpha. All right, so now we're going to look at example number 10.4. And in this example, this is an example of a rotating rod. So it tells us that we have a uniform rod of length L and mass M, and it's attached at one end to a frictionless pivot, and is free to rotate about the pivot in the vertical plane as in the figure. So it says that the rod is released from rest in the horizontal position, and then it's asking us to calculate what the initial angular acceleration of the rod and the initial translational acceleration of its right end. So this is the system right here. So you have this point is called the pivot point. Because this is called a uniform rod, it means that the mass is going to act at this point. So the M times G is acting at exactly half of the length. So the distance from this point to this point is L over 2. And so I can calculate the torque. So my angular acceleration is just given by the sum of the torque divided by the moment of inertia. So this will just be equal to mg times L over 2, because if you look at this force, so this is the only force acting on the system here. So when I calculate the torque produced by this force, if I know what the distance from this point to this point is L over 2, so I could just say m times g times L over 2, that's the torque. and then you divide that by the I value. So the I value is the moment of inertia. So this is going to be coming from the table that I just showed you. And so the I value about this point for a rod is 1/3 times ml squared. So if you plug in those values, you get your alpha to be equals to 3g/2l. Now, if you want to calculate what your tangential acceleration is, so you can calculate your tangential acceleration is just given by L times alpha, which is, so if you multiply L times alpha, you just get 3/2 times g. So this is the tangential acceleration, which is the acceleration of a point right here. All right. So now we're going to look at example number 10.6, and this is so we're going to calculate the angular acceleration of a wheel. So in this problem here, you have so this is a wheel. It has a mass m, has a radius r, and then this is connected to some hanging mass that has a mass lowercase m. And so the very first thing that you want to do is to identify all the forces acting on the system. So we can write down one equation for the force and one equation for the torque, and then use those two equations to find the force of tension as well as the translational acceleration. So what we're going to do is I want to find some expressions for the angular acceleration of the wheel, the translational acceleration of the object, and the tension in the core. So there's three quantities that we're going to calculate here. All right. So the very first thing that we're going to do is that we know that in this example here, the alpha is just the sum of the torque divided by the I value. So the torque is just produced by this force of tension right here. So it's the force of tension times the radius. So this is my axis right here. So if you solve this equation, you can get your alpha is tension force times radius divided by I, where I is the moment of inertia of the wheel. All right. So again, we can apply Newton's law. So Newton's law tells me that if the acceleration is going down, then it means that mg minus force of tension is equals to mass times acceleration. So this is my second equation. So from here, I can solve for the acceleration to get mg minus t over m. Now we know that the tangential acceleration is related to the angular acceleration by means of this equation right here. So if you substitute my alpha from this equation number 1 here, then you get, then it means that t times r squared over I must be equals to this acceleration. So if you just substitute those two together, so if you set this equals to that, and you rearrange this equation, you get your force of tension, which is equals to this. Then now that you know what the force of tension is, you can use that to substitute that into this equation here to get the acceleration. So we see that the tension force is given by this equation right here, where so I is just the moment of inertia of this wheel, and the acceleration is also given by this equation here. Then if I want to calculate my alpha, so my alpha is equals to A over R. So if you just do A over R, you get this quantity. So those are the three quantities that I was looking for: the force of tension, the acceleration, and my alpha value. Okay. All right. So what if the wheel were to become very massive so that I becomes very large? What happens to the acceleration of the object and the tension force? So when the I value is very large, we can look at this value right here. So when the I value is very large, it means that the acceleration is just going to go to 0, and the force of tension is just going to be equals to mass times gravity. All right. So now we're going to discuss how to calculate the moment of inertia, which is the I value for different systems. So we said that for a discrete system of particles, we can calculate the I value using this equation right here. So basically, the I value is just given by the sum of delta mi times ri squared. Now, if you have a continuous rigid object, then we can rewrite this equation in the form of an integral in this form right here. So this is the equation that is very important, this equation right here. So basically, the way we're going to calculate this dm is a very key point. So the dm is given by rho times dv if you have a volume distribution of mass, and so you can write your I value as the integral of rho times r squared times dv. Now if you have the mass that is like a two-dimensional, so this is the mass per unit area, then it means that you can write your rho as mass over area. If there is a mass per unit length, then it means that your lambda is mass over L, which you can write as rho times A. So again, we're going to show a few examples right here. So let's suppose I want to calculate the, so this is example number 10.7. So I want to calculate the moment of inertia of a uniform rigid rod. So we assume that we want to calculate it about an axis that goes through the center. And so you see that using calculus, I can pick a small dx here. So this is my small element dx. The distance from my dx to my center here is x. And so I know that my dm is given by lambda times dx, which is equals to m over L times dx. And so if I substitute here, so if I calculate my I value about this y-axis, it's just the integral of r squared dm. So this will be the integral from negative L over 2 to L over 2. My r squared is just my x, which is the distance from this point to my axis. So this is x squared. And then if you substitute your dm, which is all of this quantity, you end up with this. And if you do a little bit of calculus here, by the time that this integral is done, you end up with a value that is 1 over 12 times ml squared.